All right, we're rolling. Are there any questions? That moment in a teacher's life where you realize that everybody understands. Excellent.
What about all that? Question two.
All right, so. We yesterday, I do want to sort of finish up what we did, I guess, 2 days ago, but I don't remember the equations, so. Let's see, we were dealing with a RLC series circuit.
Just, which looked, I believe, and I believe we were working with it in parallel.
We did RLC parallel. Or
That would be a C there.
See, it's just that it looks like it's just.
Yeah. Following like writing too much. Sorry. Okay.
1, 2, 3, 4.
Yeah, part of this remote is.
yeah, well, yeah, I can, except for your L's and C's, but, so we had, it was parallel, so that the current coming out of the power supply, so R, L, C. And it might have been in a different order before.
Does it matter?
No. We had I sub R is 2.356 repeating amperes cosine of 376.991 T. I sub C 1.59919 amperes cosine 376.991 T plus pi over 2. IL 1.87577 amperes cosine. All that minus pi over 2. And for the power supply, 2.37 cosine 376.991 or 1.7. All right, so those were the currents that we had. And I believe we did a solution, we solved for when time is equal to 0, just to make sure that it worked. But let's actually pick a different time.
Did you copy down the one for the voltage, the power supply?
The voltage is gonna be the same for all of them, so that's not really gonna be a check. Does not want to go away. There it goes. You got scared. All right, so let's pick a particular time. Now, sometimes I'll pick a second, but let's do sometime within the first cycle. It's 60 hertz, so that the arrow is going to spin around. The phasor is going to spin around once every 60 seconds. And so let's pick a small number of t. Equals 0.01 seconds. So this is somewhat of a calculator exercise. Please make sure your calculator is in radians. Because although I put some units down, I didn't do all of them. That would be A. This is radians per second. And as you get one of them, if you just sort of tell me what you got. Gonzalez is making for some good video.
For the first one, I got negative 1.906.
Yep. Anyone else get the same thing?
For the last one, I got negative 206. Does that make sense?
It is, that's 2.37.
Oh, 2. Negative 2.066.
For the third one, no, I'm lying. There's the problem. You can take this. It's 0.9, for the second one, I'm sorry.
Second one?
Yeah. 0.939973.
9.
Yeah, they're good there.
It's also.
Okay.
For the third one, we have negative 1.1025.
Negative 1.1.
I got the same thing.
All right. So, yes, Tristan,
So the calculator had to be in,
louder, please.
you said the calculator had to be in degrees or radians?
Radians.
Ah.
Yeah, if you do degrees, you'll definitely not get a mesh here. So I have some current coming out of the power supply. So if I think about the current, and, you know, the usual SVE, coming in this way, and I'm not worried about the negative sign. Well, I'm taking the negative sign into account. I'm not worried about what the negative sign means at the moment. But just theoretically, I got current flowing out, and then it splits along 3 different paths. So the current coming out of the power supply should be the sum of the other 3. And so if we add those 3 up, so 1.906, 0.940, 1.103. Get 9, 4, 9, 3. Oh, it helps if I actually add correctly. 2 of them are negative and 1 of them is positive. So I got negative 1.906 and negative 1.103. So it gives me 9003, negative 3.09. And then I add 0.93940. Obviously, I'm rounding.
I got a negative 2.0686.
Negative 2.0.
686.
I heard 6 and then
Negative 2.0686.
686. Which hopefully you can see is pretty darn close to what the other one is. Now, physically what's going on here, if we assume a positive direction, and again, we're not talking about vectors, we're talking about what positive current flow is. So if this is positive current flow here, then at this moment, current is flowing this way across the power supply. For the resistor, it is flowing this way. For the capacitor, it is flowing this way. And for the inductor, it's flowing that way.
That's if the current goes down, or because the current is negative.
Because I just made an assumption that positive current flow is that way out of the power supply, and then if you down those, And so the negative just means that at that moment it's flowing the other direction.
Since this is AC, the way the current flows past the power supply will change
Oh, yes,
at a different time because it fluctuates, right?
yes.
Okay.
So that's why it's just at this moment, it's doing this. But notice that they're not all flowing in the same direction. So, because we get charge buildup on here, and then that, you know, there's a time lag.
Although it's probably very, very small time lag.
Well, it's cycling 60 times a second. I think we did 60 hertz on this. Oh, yeah, with that, it was 60 hertz.
So every 60 seconds the sign should flip.
Every 60th of a second, the signs flip. So at 0.01 seconds, you're still in the first cycle, and this is third quadrant. Because if we multiply 376.99 times 0.01, we get 3.76, which is somewhere between pi and 3 pi over 2. So that's third quadrant. All right, questions? Excellent. All right, so now let's take a look at a difficult one. At least what I want us to do is figure out what the impedance is, and then we can put a stake through the heart of AC power. Okay, we'll put it to sleep and then revisit it later on a master's ed or a test. This will start over here. Let's make sure I draw it correctly. All right. AC power supply. Resistor. Capacitor. Inductor. So now we don't have a pure one thing or another. It's not parallel or series, it's a combination of the two. So when you're drawing down the first phasor, it's not necessarily obvious which one you do first. And I will refer to my notes because I just remember the number of times that I go down the wrong path. Now, I know that the current across the power supply and the resistor are going to be the same. I know the voltage across the capacitor and the inductor are going to be the same. So I basically have two choices there. Those are the two phasors that would represent more than one thing. Now, when I did this before, I started with the voltage phasor, and so that's what I will do now. If we're adventurous, we could try the current one and see if we come up with the same answer, which we should, but I don't know if it's easier or harder. So I draw my phasor. And so the first phasor to recommendation, it's going to represent more than one thing. So what did I do? So I'm going to draw the first phasor right here, and this is the voltage across the capacitor and the voltage across the inductor, which I will just label as VLC, since it's the same voltage. From that, I should be able to get the current phasors for the inductor and the capacitor. Where is the current phasor for the capacitor?
Degrees ahead of it.
Okay. And for the inductor?
The opposite of that. So fourth quadrant.
And I arbitrarily made IL bigger than IC. I didn't give you enough information to actually know which one's taller, bigger, longer, faster, stronger. Ethan.
So, what made us realize that they were, like, that's where the current was for capacitance?
For a capacitor, the current leads. Remember, these are arrows that are spinning, you can think of as arrows spinning counterclockwise, and so this would be leading that, because it's ahead.
Oh, I was just wondering if there's different rules, if it's not all in series or not parallel.
No, I mean, this is still gonna hold.
Okay.
And then Eli, the current lagging. Other questions? All right, so the total current that's flowing into that junction, so I have current flowing in and then current flowing out in various colors and thicknesses. How would I find the current flowing into the junction?
Should it be the same current going across the resistor?
It would be,
Is it not that you have?
yes, you add. I have these two phasors right here, and I add them like vectors, and so they're in opposite directions, so I end up with a phasor. If L, I'm just assuming L is longer. If it's not gonna change what we're doing right now. So this in blue here is the current flowing into the junction, so that would be IL minus IC. And so that would be the current flowing across the resistor and coming out of the power supply. So we're doing sort of piece by piece. Next step. Because ultimately I've got 4 components here, I'm gonna have 8 phasors, 4 currents, 4 voltages. I have 4 currents already, because this is IR and IPS, IL and IC. I have only 2 voltage phasors, so I need the other 2. I need the voltage phasor for the resistor and for the power supply. So, what is the phasor for the resistor?
Is it not in phase with the voltage of the resistor?
I was asking about the
With-
voltage of the resistor, I
In
did.
phase with the current of the resistor?
Yes, it is. And so, the voltage phasor for the resistor would be somewhere along this line. Again, I'm drawing arbitrary lengths here, just drawing them long enough so that I can distinguish them. Therefore, what is the voltage of the power supply? Where do I draw that phasor?
The opposite. Second quarter? Quadrant.
Like where the resistor one is, right?
In phase with the current for the capacitor.
Why?
Just makes sense to me, I'm not exactly sure.
Okay. Anyone else with a different opinion?
Wouldn't it be in phase with the voltage for the resistor?
No.
Wait, no. Wouldn't we just, so if we have that one and that, oh, you have to do the rectangle box thingy and do the thing.
Okay, I do the rectangle box with what 2 sides?
But they're the ones that are on top of each other. Is what we would normally do.
The ones that are on top of each other?
Or,
Let's see if we can identify it by the phasor name.
Using the phasor using the voltage phasor for capacitor and the voltage phasor for inductor, and then using the voltage phasor for resistance. Using
Okay.
those 2.
If we think about Kirchhoff's rules, if I go across here, I'm gonna gain some potential. I'm gonna lose potential, and when I lose potential, if this were a DC set power supply, I gain, lose, lose. The sum of these 2 has to equal that. And so it's gotta be the sum of these 2 voltage phasors.
Of the voltage across the resistor and the,
Voltage across either of these, really.
okay.
So that's the phasor diagram for this. We have a certain set of rules, we've applied them. Life is a beautiful thing. But we're not done yet, of course. The head shaking no was, I wish this would never stop.
Yeah.
I assume. All right, so let's find the impedance. What is the formula for the impedance?
The current of the power supply
I'm listening.
times the epsilon sub naught. Or is it times or? Wait, no. It's. Yeah.
Why don't you start with Ohm's law?
Oh. Resistance equals V times. Or do you want it the other way?
V, change it, V equals I.
Yeah, okay, so we have delta V equals IR, but we're dealing with AC, so we just get lazy and don't write the delta. It's in there. So VR is equal to IR times R. All right, Ohm's law. Those are all capital letters because they're indicating it's the magnitudes.
Oh, so the equation for impedance is then the impedance is equal to